Morning, everybody. So this is the last usually have like one day, the last day of the school. Last week came to conclusion that people are already quite tired for those kind of material heavy things on the last day. So we decided to make a fun day a day after the social dinner, which probably also makes us quite tired. Nevertheless, I hope you are well rested, fresh mind, and well, I believe that quantum part of the school is somehow a little bit different from the other parts, because let's say quantum computation is not on such high technology readiness level as other parts of the school. Therefore, the lectures today and the transitions will be a little bit more on the theoretical side to give you some view of what quantum computation is about, and a little bit less on the remote sensing, but we'll have also some references to remote sensing. One more thing, so as I said, quantum computation is at a little different state of development than classical computation, AI, and so on. So the learning objectives for today is mostly to expose you to the idea, to explain the basic rules, the principles, and to allow you to understand the jargon, the notions that people use in quantum computing, and maybe make your mind about the whole technologies behind it. So my name is Artur Miroszewski. As Laura mentioned, I'm from Jagiellonian University, Poland. I'm a part of a Quantum Cosmos lab there, and I know more importantly, I'm a part of the recently established Quest technical committee within the structures of IEEE GRSS. Quest is quantum science and technology. Currently, we have Gabriela, who is here, that he hosts he's the chair of the technical committee. We have two co-chairs, Andra and me, and we have two working groups: quantum sensing for Earth observation with Amer and Jan. And also we have quantum computing for Earth observation working group, and actually all the chairs are present here, I think, of the working group of quantum computation for So we've started, I think officially we've started this year, right? So we are quite recent thing, and we are part of this school. We are organizing different variety of activities. This year, I will also organize one workshop on quantum computing space applications. And well, if you're interested, you can scan the QR code and join Quest, or just Google IEEE Quest or IEEE GRSS Quest and find the website you would like to join. Okay, going back to the course itself, that's the schedule for today. I will start with hour and a half of theory story. And I'll try to make it as entertaining as I can. Then we'll have a break with a poster session, right? Then after that, there will be half an hour of a lecture about quantum algorithms. So basically, during the introduction to quantum computation, I will introduce the basic postulates, principles, what is measurement, blah, blah, blah. And in the end, I will introduce the quantum gates and circuits. And with the circuits, it will be a great moment to focus on quantum algorithms, so make those circuits bigger and see the logic behind the quantum computation and classical, and well, the differences with classical computation. And then we'll have lunch, and from the, sorry, there's also a hands-on session number 1, which will be run by IBM remotely with our help on here. Lunch, and then Amer takes over. Amer is there, you can see his photo here, and he'll take over with explaining to you what quantum machinery is and how it can be used in remote sensing, and I'll break and hands-on session run by Amer. Okay, so just to set the expectations, well, quantum in general is a very broad topic, and for most of the time of the, say, last 100 years, because it's already, quantum mechanics is already 100 years old, it was mostly discipline in which physicists contributed the most. Me and myself, I'm a physicist, and well, we are able to establish a whole set of theories based on idea of quantum. However, the whole thing that is present on the slide will be a material for bachelor or maybe bachelor and master's studies at the university, so we don't have time for that. Well, within the most broad subject, as I would say, quantum field theory, we have quantum mechanics, which is a smaller subset of the quantum field theory. It's a non-relativistic quantum field theory. Within this subject also, we have a smaller set of topics devoted to quantum computing. This infinite-dimensional hyperspaces can belong to quantum computing, but will not care about it. We'll stay with the finite-dimensional problems. And well, quantum computing by itself is already a quite broad subject that would take at least 1 or 2 university courses. So again, not possible for today. But I tried to find the smallest subset of quantum computing that will give you some hopefully good understanding what's going on. Okay, so we'll drop some of the topics. They will be probably mentioned, but will not go deep into topics of noise, quantum channels, or error correction. Okay, so let's start the theory part. Just a math reminder. The language of quantum mechanics is the language, in the language of quantum mechanics, we use complex numbers. So hopefully you've seen complex numbers before, but just to remind you, what a complex number is. So complex number consists of basically 2 real numbers. The real number here A and the real number B, which multiplied by the imaginary unit I. Okay, so it's somehow like a 2-dimensional real number. Sometimes in engineering people use J instead of I, but I think the I is more common in general, so I use I. And well, the imaginary unit is defined in such a way that the square of I is -1, so we can say that square root of -1 is I. And the basic operations with complex numbers is the complex conjugation, which basically flips the sign of in front of I. We can take the real part of the complex numbers with A, imaginary part basically B. And we have basic operations like addition, which is very simple in this form because we just add real parts and as imaginary parts, and multiplication, which can be a little bit harder in this form of complex numbers. And mostly, well, quite importantly, we have the modulus, so the same magnitude of the number. Yeah, well, as I gave you a simple example, but I don't think you have to go deep into that. And there's another way to represent complex numbers, completely equivalent. Instead of real part and imaginary part, one can divide the complex number into modulus, so the magnitude, and the phase, which has which is exponentiated I with some argument. You can easily flip between those two forms, but why this form is quite useful? Because multiplication is extremely easy in its polar form. You just multiply the magnitudes, moduli, and add the phases. And there's a very nice little representation of the complex numbers in polar form. There's R magnitude, so this distance from the origin of the x and y axis, which is real numbers, and the real part and imaginary part of the complex number, and the phase, which is the angle from the x axis. Okay. One more thing. One more thing. We can put complex numbers into matrices. And when we do so, we can, well, basic operations on matrices is done transpose, so we basically flip everything along the diagonal. Complex conjugation, we just perform complex conjugation to each of the numbers in the matrix. And probably the most important Hermitian conjugation, which is symbolized by this cross, which is basically transposition and complex conjugation. So we flip and conjugate the elements. We have standard matrix multiplication, and what is like the heart of quantum mechanics. We'll use matrices to represent states, operations, and we have to remember that matrices, the order of application of matrices matters. So we sometimes introduce commutator. So the difference between what happens when you first apply M1 M2 matrix, then M1, and the other way. And there are two very special types of matrices we'll talk about today. The Hermitian matrices, which have the property that they are the same as their Hermitian conjugation. And well, they are the generalization of symmetric matrices, and unitary matrices, in which the inverse matrix of U is the Hermitian conjugation of U. Okay, and those can be seen as some kind of rotations in the space that I'll introduce right now. Okay, and we'll have to go through 3 postulates of quantum mechanics, and then we'll go into some, let's say, more fun, hopefully. But nevertheless, we have to set the stage. And the first postulate of quantum mechanics, which is... Okay, so actually I tried to make those postulates more quantum computing important than in general quantum mechanics true, but they are still true, so don't worry, they are a little bit simplified. The first postulate is to actually, how do we describe our system? How do we describe the state of our device? And that's what postulate 1 of quantum mechanics explains. So in quantum mechanics, the state of a physical system, in our case the quantum device or quantum computer, is represented by some vector in some Hilbert space. Okay, Hilbert space, I don't know if this days will be that important, but it's some kind of a vector space with an inner product. And people in quantum mechanics use a very specific notation for vectors, which is called bracket notation. And standard vector that we use is called ket, and is represented by such a symbol where we start with a horizontal line, have some usually Greek symbol for the actual state, and this angled right brackets. And we can multiply vectors with inner product. So the dual, so the one with vector with which will multiply is called bra. So together bra and cat makes bra cat. That's the humor of physics, sorry. But we'll get to that, and not the humor, the multiplication. Basically, well, customary, the first state that we've chosen to represent is written with 0, and on some the d-dimensional space, well, you can also write it as a column vector with just 1 as a first coefficient, and a coefficient and zeros everywhere else. The next vector, the basis vector, can be, well, written as 1, and 1 is on the second coefficient, and so on, so on, so on. So we have a basis for the linear space in such a way. And with the dual vectors, we basically can obtain dual vectors by taking a standard vector and doing Hermitian conjugation, which just does the complex conjugation and flips the column vector into the row vector. So we can use basically the standard multiplication of vectors for the multiplication of quantum states. Okay, and the first thing that will actually, the first difference that we'll see between the quantum computing and the classical computing, maybe I will just write something, one thing more. In general, the state of a classical computer can be represented by bits, right? And we have some state 1, 0, 0, 1, 0, 1, 0, 0, 1, 1, okay? The analog state of in quantum computation will be basically the same, as you'll see soon, but in the bracket notation. Okay, so we can obtain the analog in quantum computing of the state of the classical machine, but something that we cannot do in classical computation is to make some kind of a linear combination of such states. Okay, we can add those things, but they will in classical computing either the classical computer is in such state or some other with some other bit values. In quantum computation, we have the principle of superposition, that the quantum computer can be in a state which is a linear combination. So this is possible linear combination of some basis vectors. Okay. And that's basically the first thing on the slide, is that, well, when we take basis states from 0 to d-1, we can add them and put weights to each element of the sums. But we can, for example, create 2 subvectors, and as I said, bracket the inner product between those vectors. So multiplication, if we have the basis like this, so orthonormal, so those vectors are perpendicular to each other, we can introduce a conical delta, and basically the multiplication between 2 vectors is complex conjugate of the coefficients of the first vector times the corresponding coefficients of the second vector. And in order to maintain a probabilistic interpretation of quantum mechanics, which, okay, we'll go back to that, we customarily normalize each state to 1. Okay, and okay, state examples. The very general one is just with some weights, alpha 0, alpha 1, blah, 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 so on. The more concrete example, 5, 1, just like this, okay? So the first state, some second state, third state, fourth state, and so on. 5, 2, again, with some weights, and well, we can write them as column vectors and multiply one with another. How do we do that? Well, we just take the coefficient in front, and then multiply corresponding coefficients. Remember it calculate one of the vectors. So in this case, by sorry, I didn't find calculated, so it's the click. Okay, yeah. So I prepared some exercises, but actually there are placeholders to check if I'm on time. I'm already late, so I will just, this will be example one, not exercise one, okay? So I asked in the example that we have such two, such a state on two basis states, and we would like to normalize it. So to find such n that the norm of the vector is 1, and then I will ask if n is unique. And how to do it? Well, I will explain it to you right now. Well, we have to multiply the vector with itself, which is, this is the rat, this is cat in here. We get, as this is a complex conjugation, well, we have to take a modulus here, and we get that, well, the modulus of n is square root of 26, and, well, it's a modulus of n, so that I mentioned that we are dealing with complex numbers, so basically, well, we can choose n to be square root of 26, but we can add basically arbitrarily complex space to this number. And what can be surprising is that no matter what kind of phase we add to the, so the modulus is important, but general phase doesn't matter in quantum mechanics at all. Okay, so anything that we'll observe will not matter on this number that we can additionally add. Okay, just a second, I'll just check how I'm going. I don't see my numbers, that's okay, I can see. Good. The most important state, let's say, of system in quantum computation is qubit, which is basically a two-state system. So basically what we've seen here, with arbitrary coefficients in front of the first basis vector and the second. From normalization condition, we know that those two things, the moduli squares, sum of moduli squares of alpha and beta is 1. And the examples of substate, so if we take beta to 0, we just end up with state 0, so the first basis state. If we go with alpha 0, we end up with 1. And there are other very important states. If we take the 1 over square root of 2, 1 over square root of 2, we have a very special state called plus state, because we have plus between the two basis states. And if we take square root of 2 minus square root of 2, with the coefficients we have a minus state, and some other possibilities are present. And knowing that those two things have to be normalized, we can use the standard trigonometric identity that, well, sine squared plus cosine squared equals to 1, okay? Plus the things that we are dealing with complex numbers, so we can introduce additional phase. And there's a very nice geometric interpretation of qubit, of the qubit state, called the Bloch sphere, in which we, on the north pole, indicate the state 0 of the basis. On the south pole, we show the first state, or the state 1 of the basis, and all other states which are parameterized with phi and alpha, or alpha and beta, lay on the surface of such a sphere. And for example, well, you can already see that 0 state and 1 state are, well, on the north and south poles, so along the z-axis. But the states that I already introduced, the plus and minus, for example, are the pole states along the x-axis here, so plus and minus is here, and the I plus, I minus, not that important, is along y-axis here and here. Okay? We are finishing on the first postulate. It's the longest one. So we can make a composite system. So just one qubit is not enough to impress anybody, really. So we can take 2 qubits, 3 qubits, 4 qubits, hopefully 1,000 qubits, or even more, hopefully million qubits together. Okay? And the surprising thing is that if we take the dimension of qubits when we compose them together does not add but multiply, which means that well, in the case of 2 qubits, well, it's the same as we would add and or multiply, because qubit is two-dimensional system. Two-dimensional systems can be either 2 plus 2 equal to 4-dimensional, or 2 times 2, which is also 4. So that's not the best example. But if we take 3 qubits and compose them together, we get not 6-dimensional state, but 8-dimensional state, and so on, so on, so on. So the dimension on which we operate scales exponentially, not polynomially, in the number of qubits. So we have, in general, 2, and it will be a number of qubits, and the dimension on which we operate is 2 to the n. So it grows very, very fast, and that's one of the most important properties of quantum computing. Customarily, when we compose 2 objects, 2 qubits, we use this sign of a tensor product, which is this kind of a light bulb, let's say. Or we can just skip it. It usually quite clear from the context in those 2 ways. Yeah, and so we can introduce how we obtain the coefficients of such state. But well, the thing is that if we compose 2 states, and if we would restrict ourselves only to product states, so states of this form, then we will actually add their dimensions. But within the quantum mechanics, we have also possible states, which are called entangled, so they cannot be written in such form as one state times the other. And a famous example that you will see during hands-on session, I believe, is a Bell state, Bell plus state, which is state 0, 0 plus 1, 1. Okay, so the first qubit is it's even hard to say properly, but the first qubit can be in the state 0 or 1, while the second qubit can also be in state 0 and 1, but only if the first, it can be 0 only if the first qubit was in 0, and it can be 1 only if the first qubit was in state 1. So in general, with a product state, well, we can say that this subsystem has a property phi, this subsystem has a property psi, phi, and they are a little bit separate. But with not a product state, but an entangled state, you cannot distinguish between those 2 subsystems. They have very strong correlations with each other, and you cannot even say, in fact, that one subsystem has a specific property, right? You have to speak about the whole system, or the system as a whole, and that's actually what makes this scaling such of dimension such high, because there's lots of those states in the Hilbert space. Okay, exercise. I will also use it as an example. Okay, so we have 2 states. They are not normalized, but we don't care about normalization right now. It's not that important. Can you? Okay, it's a tricky question. Can you guess which one is a product state and which one is entangled? Anybody? I know it's morning, so I will just give you a minute and then I'll explain. It's the I think that there's a very advanced formula for that. I think that would be useful. Get it? and this actually is A minus B, A minus B, and so on product. And with that, I just conclude that exactly. So this state in this mixed terms, 0 and 1 and 1, 0, have minuses, just like in such formula, while pluses in front of the, let's say, square term, 0, 0, and 1, 1. So we can indeed write it as a product state of 0, minus 1, 0, minus 1. So something like this. And the other one has this one specific minus, which is actually just a phase, and well, you would not be able to write it as a product state. So this second, the phi state is a function. Okay? But that's not that easy to just look and see which state is an angle and which is not. Okay. So we know what state of our quantum computer, how we can describe the state of our quantum computer, but the state is not everything, and I will mention this on the next slide. You can see very complicated slide. We have to, well, in classical computation, well, the classical computer is in such state, and we automatically assume that, okay, so if it's in such state, then we know it is in such state, okay? Then we know in what state is our classical computer. And that's not actually true for quantum computing, because there are two different, let's say, words. The mathematical modeling of the state of the system and the actual state of the system that we observe, okay? And that's what postulate of measurement explains. So a little bit more advanced statement is that for every physical quantity, we can introduce a Hermitian matrix A, which eigenvalues will be the measurement outcome of the state in which our quantum computer is. And we can also add a Born rule of how frequently each eigenvalue will see. So if we have a quantum computer in the state psi, okay, and we would like to see how frequently we will find the eigenvalue of the matrix that we are measuring with respect to AM, we have to project the state in which the computer is onto the eigenvector corresponding to this eigenvalue, and the moduli square of such an inner product is the probability that we'll see this outcome. Okay, that's a little bit complicated, so I'll go through examples, I think. Yes, but that's something I would like to stress out, that quantum mechanics without the measurements is a purely mathematical theory that we believe describes how universe works, but without measurements we cannot access to actually validate what happens underneath, okay? The system is in some state, as we believe, but, well, we believe so, okay? That's all. And what actually embeds the quantum mechanics in the real physical world is the measurements. When you look at the state, we infer some information what our quantum computer, in what state it is, but through the measurement, we do not see the whole state, but just one eigenvector. So, for example, if this was a whole linear combination of different basis states, what we'll get after the measurement is just one component of such state. this one or that one or some other, according to the probability with respect to these weights. Okay, and that's also a source of some misinterpretations of quantum mechanics that we will see soon. That people say that we can apply this linear combination of different states. So we have this whole linear combination of variety of input states at the same time and apply some function to it. And we can, with one computation, we can apply, for example, calculate the function value for each possible input, which is true. We'll end up in a state which calculates this function. We'll get a linear combination of the outcomes of each possible output of the function in one state, but we'll not be able to access it as easily. That's what people call quantum parallelism, and it's, well, quite frequently misinterpreted. Okay, just to make some connection to the quantum computing, if we have some basis states in general, what we'll look for in the measurements will be a specific state K, which is, well, basically, well, if we have a linear combination of such states, after the measurement, the whole linear combination will collapse to single one of, well, just single of those basis states with some probability. Okay, so the quantum computer, let's say, is a probabilistic machine, and usually we have to run the circuit many times to estimate how frequently it will see this state and this state and this state and so on. Yes. So it's a bottleneck for one computation. Okay, Hermitian matrices as observables. Maybe I will go a little bit faster here, but very important three Hermitian matrices I would like to introduce to you is X, which is maybe Z first, which is actually in the computational basis that we introduced is already diagonal and has two eigenvalues, 1 and -1, as you can see. X, which flips the state, quantum state from 0, basis quantum state from 0 to 1, from 1 to 0, and Y is, well, because I choose Y only because it's part of so-called Pauli matrices. Okay, and that was quite heavy, the whole thing was quite heavy on the theoretical side, so I'd like to propose an experiment. I'm a physicist, so I believe experiments are cool, okay? I don't know if you've ever heard about the company called Polaroid. Yeah, I think that they've invented, well, I know that they invented something like this quite a long time ago, which is a polarization filter, okay? By itself, one of those, well, you see that it's a little bit dimmer, the light coming through it, but why is it dimmer? Because actually the polarization filter allows the light to pass only if it has a very specific polarization. Maybe I will even show something. When we have well, you're in the remote sensing field, so you know everything about the electromagnetic spectrum, but if we have a light ray that goes this way, well, it's basically composed of the combination of electric field and perpendicular magnetic field. I'm not very good at those kind of things, but hopefully, okay. This is perpendicular magnetic field, okay, and the
It sees the different now. It sees something bigger.
Good job. Good job. Oh, okay, good. Thank you. And seeing in which those fields directions are oriented sets our polarization. Okay? And what polarization filter allows us to do is to filter out only light rays which have very specific polarization. Okay, that's easy. How do we check if this is, I'm not scamming you and it's just a dark foil? Well, semi-transparent foil. Well, you have to take the second polarization filter, apply it the first one, and rotate. You'll see that if I align those two polarization filters in the same polarization direction, basically it allows the light to pass freely without making it, well, after the first polarization filter and with with two polarization filters, basically they are a little bit dimmer but of the same light intensity. If we rotate those two things, well, with respect to each other, you can see that this is orientation of the filters, which is one, for example, vertical, and the other is horizontal, which actually means that the first filter passes only the vertical light, the second allows to pass only horizontal light, but as the first one allowed only the vertical light to pass, then it means the second has to block all the light that tries to pass through it. Okay, that's quite easy. And well, there's a classical explanation for such a phenomena, but actually the whole mathematical talk that I gave you serves a very good purpose here, and the whole idea can be explained with the vectors in the Hilbert space. Okay, so if we introduce two basis states, not 0 and 1, but v and h from vertical and horizontal, we can describe any setup of the polarization filter by an angle theta, which basically means that I've rotated a filter a little bit, and the polarization of the photon, rotated photon, can be written as a cosine of the linear combination of vertical and horizontal. So, for example, the 45 degrees at the angle of 45 degrees, we will have 1 square root of 2 vertical, 1 square root of 2 horizontal. So this will be such a setup. Okay, and the question is, can we describe the intensity of light with respect to the vectors that I've introduced? And yeah, exactly. So using the measurement postulate, which measurement device will be the last polarization filter, we can describe the state. So after the first, well, we start to countpolarize light here in the room. After the first polarization filter, we'll get the state, let's say V, if we assume that this is vertical. And if we add the second filter, which allows photons, only horizontal photons to pass, we can see, so how many horizontal is in V? Well, it's 0, because those are two orthonormal states. So we know that the intensity of light will be proportional to something like this, which is 0. And the absolutely fantastic thing, in my opinion, is that I can do something like this. And ta-da-da-da. If I put one filter in between, I actually allow, I don't know if you can see it, allow some light to pass through it. Okay, so it seems quite counterintuitive, right? Because after the first filter, we have only vertical light. Okay, and well, this one should just filter some part of the vertical light, the vertical polarized light, but the last filter should block like completely the whole spectrum, right? Because well, we had only vertical light after the first filter, but that's not what happens, right? Actually, when I do something like this, it goes down again. Okay, so this is well. We'll see how it works with the vectors in Hilbert space. Yeah, this is the setup. And okay, after the first filter, we have just vertical light. Then, well, we have to think about how to describe the system with the tilted filter, and then we get the horizontal. And in order to find the vectors which will pass through tilted polarization filter, well, we can use the basis of vertical and horizontal, and use the angles coefficient that I already introduced. So let's say it's tilted at 45 degrees. So the state of 45 degrees polarization is 1 over square root of 2 vertical, and the same for horizontal. We can introduce in order to introduce a basis with orthonormal vertices, one subvector, one such, which is perpendicular, so minus 45 degrees. And well, we get that, well, we invert the relation and we get the V polarization consists of equal superposition of light going like this and light going like this. And well, we can calculate that, okay, so after the first polarization feature, we had a vertical state, as we already stated. Then the second one is 45 degrees, so we can project one on the other and get non-zero value. Okay, and after the second polarization feature, our light, part of the light, because there's some transmission coefficients, becomes polarized in this way. So actually, the measurement changed the state of the system from being this to this. So we rotated our polarization, and we can see, okay, so how this polarization is probable when we projecting on the horizontal feature, and this not zero, again, 1 over square root of 2, or 1/2 in fact. So in total, we get something, well, maybe a little bit strange when you first think about it, because non-zero polarization, non-zero intensity, but, well, we can explain that with the two postulates of quantum mechanics that, well, we, after the measurement changed the state of the system throughout the whole system, and we were able to rotate polarization with 3 filters from this to this and this, okay? And well, for me, it's always, every time I do it, I'm like, whoa, really? Okay, that's, yeah?
As Speckmann was saying, use 4 and 6 or drive the chips or that they pose to the way to become political. So.
Yeah, okay, so you mean to introduce like additional steps, right? And just rotate a little bit. Yes, and it will, I believe it will become darker and darker, in fact, okay? And that's because when you, let's start with a setup like this. And let's put it on 45 degrees. When you rotate it, we to a, let's say, smaller relative angle with respect to one polarizer. Actually, the component with respect to, let's say, vertical, okay, it's actually bigger, right? So, well, actually, we have to calculate that, okay? Let's do it, we can do it during the break. The additional factor which will be important is that, well, there are some losses, right? So let's say adding lossless polarizing filters can lead you to, I think, the same result, I would guess, but we can calculate that. Okay? Excellent question.
You can.
You can. That's exactly the same thing, right? But with additional steps. That's a good exercise, by the way. I will tell you by the end of the day, okay? That's a challenge. Yeah, okay. The last postulate, which is important. So we know the state of the system and how to read out the state of the system. But, well, having the system frozen in time is useless. We want to perform computation, okay? And that's what first postulate is about time evolution. And I told you that, so there are two types of matrices that are important. Hermitian, which are important for measurement, and unitary. And unitary are important for the evolution of the system. And well, in general, in quantum mechanics, there's a notion of Schrödinger equation, time dependent, and so on. But in the quantum computation, we will actually discretize time, and each time step will be the application of single unitary operation seen as a gate, okay? Like a logic gate in the let's say, low-level classical computation. So that's how we'll evolve the system. We'll apply gates to some states, and in this way change the states. Okay. And that's exercise I will maybe use again as an example, but I will calculate it on the blackboard because it will be easier to follow, and again, it's quite interesting in my opinion. So, one of the big differences between classical and quantum computation is about copying the state. And we'll prove something right now. Let's assume that we have a gate which is able to, when we have a system composed of two subsystems, to copy the first state, arbitrary quantum state, into the second subsystem. Okay? The very basic operation in classical computing, just copy x to y or something like this, right? And let's see what happens when we assume that we can do that on with a quantum computer. And let's do it for a simplest system. So there's one qubit state and some other one qubit state prepared in the zero state. Okay, so a system composed of two qubits, a product state in this case. And well, let's first apply this u. I'll write u instead of UCL to, okay, no, maybe that's right. Psi state is equal to what we have assumed is alpha 0 plus beta 1. So that's what we want to copy. Okay? And from the assumption, u acting on psi times 0. From the assumption is psi times psi times psi. So it will be alpha 0 plus beta 1. I will change the notation, drop the light bulb here. So, but it's here, right? Alpha 0 plus beta 1, which is alpha squared 0, 0. Let's go with this one, beta squared 1, 1. Plus mixed terms, alpha 0, 1 and 1, 0. So it's alpha beta 0, 1 plus alpha beta 1, 0. Okay, so that's one way to calculate it. And the other way is to apply UCL from the start to this state. So I already used much of the space, but the second you'll see, right? Yeah. U applies to the state alpha 0 plus beta 1 product with 0. So we do not apply u now first, but first we'll compute calculate the state inside this square bracket. U is equal to alpha 0, 0 plus beta 1, 0. And now we'll apply u, but unitary operators or unitary matrices are linear. So it's actually alpha u applied to 0, 0 plus beta u applied to 1, 0. So alpha, and we copy 0 to 0, so 0, 0 plus beta, and we copy 1 to the second register, so 1, 1. So with the same computation, without breaking any rules, we have obtained two different results, right? And well, that's strange. And that's actually this proof by reductio ad absurdum, right? Or something like this, which basically means that, well, such a thing that copies one state to the other register does not exist in quantum mechanics. We cannot copy states in quantum mechanics, which is a huge bottleneck. But there are ways around it, okay? So one of the easiest proofs in quantum computation, but also one of the most profound, You actually can right now perform and let's say brag without your friends. Yeah, I know that you can copy states in one computation. Yes.
There's one thing from my person that's not really super excellent.
Yeah.
Sometimes we said that, say that qubit can be called in the, sense that it is not wrong to say to copy qubit. Here it's wrong to say that it's wrong to copy qubit, or which is not really a copy operation.
Well, this is a copy operation, but I would not say a copy a qubit, because qubit is it's a two-state system, so maybe you can say that, well, okay, I just think about the language. Usually you say copy a state, right? But qubit is
Since probabilities are involved, usually when we read something, we read that the one characteristic of the qubit is that it can be copied in the exact status which it is. So that's why I'm just asking to understand.
Well, I mean, yes, that statement is correct. We cannot copy, but what do you have to arbitrary qubit? Okay, that's you cannot. If you have some qubit in an unknown state, you cannot guarantee to move this state to some other register if we don't know what kind of state it is. Okay, so I don't know if I answer your question, but if I hear that someone says you can copy arbitrary qubit, I say no, you can't, and that's why. Okay, but we'll get to that we can do something around. Okay, we can go around a little bit, but that's not copying arbitrary state. That's the solution, let's say. So then we obtain the no-cloning theorem, which basically says what I said, but for any state, not only one qubit states. Okay, and we are on time almost, and we'll get to actual computation, but in the simplest case. So simple gates in quantum computation, okay? And the simplest gate we can apply to our system is the one qubit identity gate, which sends state 0 to 0, 1 to 1. Its identity does not do anything. If you want to write it, and I'll show how to read gates in a bracket notation, is let's see, identity gate is 0, 0 plus 1, 1. And if you apply it to any state, commercially, let's say, okay, let's just to focus our attention, let's not treat it mathematically rigorously. What it does, it looks at the state 1 in this vector and sends it to state 1, and looks at the state 0 in this superposition and sends it to 0. Okay, so that's how we read the gates, what they do, from this side to this side. And in the matrix notation, well, identity gate is identity matrix, right? And in computation, nobody writes identity. It's just a wire, okay, without any gate, because it does nothing. There's the NOT gate, which is a generalization of the classical NOT gate, which flips state 0 to 1 and 1 to 0. So if we write it down, it will be sending state, maybe I'll start here, state 0 to state 1, and sending state 1 to state 0, and the matrix for such gate is such, which is Pauli X gate that I introduced before. Okay, extremely important gate, which now introduces some more quantum mechanics into those gates is the gate that changes the state 0 and 1 into different bases of star of a state plus and minus. And well, this is a plus state, and this is a minus state that I introduced some time ago. And that's exactly what I said. So from 0 to this linear combination, and from 1 to this other linear combination. And it's an extremely important one-qubit gate, because if we compose many of those gates on different qubits, we'll get from the state 0, 0, 0, so usually the initial state, into the full superposition of states. Okay, so the state Iceland with Hadamard transform, so Hadamard on each qubit register will be 2 from 0, 0. Let's not care about normalization. Will give us the state 0, 0 plus 0, 1 plus 1, 0 plus 1, 1. So extremely efficient way to get access to all states of the that we have available in our hyperspace. And okay, there was a question exercise S-gate, phase gate, so-called. From the truth table, can anybody see which matrix representation it will have? Don't be shy. So it sends 0 to 0, so we know that this element will be 1. Okay, that's useful. It will be this one. Okay, it sends state 1 to I, right? So that's the phase gate. It's not that important, but I just wanted to show how to do it. Okay, remember block sphere? So that was a geometric representation of a one qubit state. And let's see what the gates do to block sphere. And in general, this is a NOT gate, but we can apply, well, we can't exponentiate that, okay? And there are efficient ways to apply such gates subsequently. And what NOT gate, not surprisingly called X, does is rotates our state along the xi axis, so this way. Okay? What one exponentiated y gate does is rotates the state around y-axis. Okay? That x gate by itself just rotates it by 180 degrees, so just flips it on the gate. Y does the same, but throughout different direction. And Z gate, well, does the same, but around the direction of the state in the computational basis, so does not change anything. Okay, and we can compose gates, for example, Hadamard. So set from state 0 to plus, and then rotate around the Z-axis. Okay, so those are what basic gates do to the state. And yeah, we have 15 minutes, which is fine. If we would apply only single qubit gates to our qubits in the system, there will be only product space, okay? Which means that we'll not have access to the whole Hilbert space. That's why people introduce two qubit gates that entangle two states, different qubits together. And the simplest two qubit gate is a control node gate, which, well, there's on one qubit, the qubits are represented by horizontal lines, so one qubit here, one qubit here. One qubit is a control, and one is the target. And whenever control is 0 state, it does nothing to the target. So from 0, 0, it goes to 0, 0. From 0, 1, it goes to 0, 1. But whenever control is on its change state 1, it flips the target state. So from 1, 0, 1 is control, 0 is the target, it goes to 1, which is control, and 3 target 1. And from 1, 1 goes to 1, 0. Okay? And that's how we entangle together qubits, and in this way we can obtain states which are entangled. And for example, if we use Hadamard gate here and get the state here as a linear the plus state and do the control node operation, we'll get one example of an entangled state that I mentioned, the bell plus state. Okay? And that's something we would not be able to achieve with single qubit gates. And we can do it even further. That we'll see that actually it's some kind of a copying, right? That if you apply C0 to the system of some arbitrary qubit times qubit in an initial state, it will act in such a way that you'll get the same weight, but with respect to the state 0, 0 instead of just 0. So it's copying or extending the basis state, and beta with 1, 1. And we can actually apply further to more and more qubits, create this ladder that will copy the qubit to, let's say, extended basis states, and that's extremely useful for error correction that I told you I will not mention. So sorry, because if one qubit flips in such a system, we can use a majority vote to correct it, right? If we have in state, we know we have allowed only state 0, 0, 0 and 1, 1, 1, and we end up, because of some noise in state 0, 1, 0, we say that we likely had state 0, 0, 0, but there was some noise applied that flipped one bit, so there's this majority voting. Very useful for error correction. Okay, control Z gate. Well, basically very similar, but we apply Z gate, so just flip the pace of the target qubit whenever control is on. And that's something with which I will finish my theoretical part. The Toffoli gate. So we can apply, we can use controls on many qubits. So apply control to one qubit, to this bit. Does it still work, right? This. To first qubit, second qubit, and use a target as a third, on a third qubit.
One on the top.
It stopped working, right?
Yeah.
But nevertheless, I always scream, so probably you'll still.
We have to record it.
Okay, recording. Maybe this will be, a secret knowledge now.
I do battery, I think.
Okay.
Try again. Yeah, but it's battery.
Okay. So, that way. Okay.
I do battery.
I have such a power draining voice. I hope that I didn't drain too much power from you today.
That's a red light, so I suppose it's battery.
Red light. Stop talking, Artur.
So one will have 5 minutes more.
You have a replacement for that? Because I have 2 batteries in my hotel, but it's like 10 minutes work.
Speeds.
So we'll have one more profound result, and then I'll talk a little bit about the practicalities. But let's not get ahead of
Green light.
Green light.
You can go.
Yeah. Sorry. So we can create pre-qubit gates in which, for example, we have 2 controls and 1 target. And in general, we'll have 8 operations, 2 to the power of 3. But I will fix the last state, the target state, to be 1. Okay? In such a way, we can just consider 4 operations. And when you have 2 controls, it works like AND, okay? So it will, the first qubit will apply action to the first qubit only if both controls are on, okay? And let's see. Okay, so I fixed first qubit to be 1, so it's 1, 1, 1, 1, 1, 1. And let's see how different setups of A and B or first and second qubit work. So if it's 0, 0, well, it does nothing, okay? If it's 0, 1, it's still 0, okay? Because it's end between 0 and 1, so it's 0 does nothing. 1, 0, the same situation, does nothing. And if all are 1, both are 1, 1, and the third one is 1, we apply the gate, and it will flip the 1 to 0, okay? Quite simple. However, it has some profound results, okay? Because if we forget about this qubit in the input, and then forget about those qubits in the output, okay? So basically, we can say that those two qubits are input qubits, and this one is an output qubit. We'll see something nice. 0, 0, we will apply 0, 0, apply gate to two qubits on say 0 and 0, we'll get 1, 0, 1, 1, 1, 0, 1, 1, 1, 0. And this is exactly the action of the classical NAND, not AND gate, okay? And I'm not an expert on classical computation, but I heard that application of NAND is universal. We can construct any gate just from NANDs, okay? So the result is that we can, any computation that can be done in classical computing, okay? Any computation that can be done in classical computing, it can be done with NAND gates, and as we can do NAND gate in quantum computing, then quantum computing can do the same computation as classical computing, okay? So we can recreate any classical computation with a quantum computer, which is quite a strong result, okay? And actually the vice versa works also. We can do all the computation that quantum computer does, we can simulate it on the classical computer, which we will do on the first hands-on session, okay? Okay, yeah, let's not get that ahead. There's one thing I would like to add, is that I told you that unitary gates can be seen as rotations. What I meant by that is that any unitary operation is reversible, okay? And that's true, okay? And that's important because most of the operations we do on a classical computer are not reversible, okay? Let's take 2 plus 3. My extremely advanced skills in maths says that it's 5, okay? And if we know that the result of the addition is 5, okay? But we don't know that, I will cover it. We actually cannot reverse the operation because we don't know if 5 is a product, well, is the sum of 1 plus 4 or 2 plus 3, right? We don't know that because we don't know with what we started. That's not non-reversibility of classical computation. That's something we cannot have in quantum computing because of this unitary evolution. So the trick to go around it is to use ancillads or the additional registers that we do not measure after computation. So we know that the whole operation was unitary, but if we forget that we don't look what happened here, then our knowledge is not enough to reverse the computation because we don't know what was the starting state. However, we do not break physics because this operation in general was reversible, but we just don't know we didn't look at the whole system, right? We just dropped some information about the whole system, and that's the way to, let's say, go around this irreversibility of classical computation. Summary, and we'll be almost out for time. So that was quite a morning, right? Especially after the social dinner. So I just to summarize everything. So quantum computation is described using the properties of quantum mechanics. So the state of the computer is described with vectors on a vector space. And M evolution is described with matrices which are unitary. The outcome of computation is obtained by measurement, and actually usually we get just a portion of information about the system because it just collapses to one state of the whole linear combination of states. And that's actually both the points here. Well, we have access to exponentially large Hilbert space, so we have some advantage here, possible advantage here. So very expressive computation. The unitary transformations are already mentioned. Reversibility of computation, although we have a way to go around it. And any classical computation can be implemented on a quantum computer. And I told you that vice versa. So simulating quantum computer can be done on classical computer, but in general we'll have to have 2 to the n dimensional vectors, which is very hard to calculate, well, in general on a classical computer, right? So we use the, let's say, naturalness of evolution in such high dimensional spaces of quantum computer, which is not natural for classical computers. So the whole idea of what can be done better with a quantum computer is not about doing something a classical computer cannot do, okay? It's about doing something which classical computer cannot do efficiently, okay? So it's all about basically speed up. Talking about speed up, last 5 minutes please, okay? How do we realize a qubit physically? And there are actually different methods. One of the most popular is using superconducting quantum processor. You probably already heard in yesterday's talk on the refrigerators and so on. That's the superconducting thing. I would not like to describe the physics of it. It's based on the Josephson junction, which is a very specific quantum system. However, there are trapped ion quantum computing and neutral atom quantum computers, which basically use physical systems of, that's one of the worst ways to write an atom, but somehow it's stuck to textbooks. That if we say we have an atom, an electron around it, so let's say like hydrogen atom, 2 states of the system can be described by electron being on the first orbit or electron being on the second orbit. Okay, that's a physical realization of the qubit in these trapped ion computers. Usually, there's a third orbit quite far, used for measurement, right? And looking at the light emitted by going from here to here or from here to here, you can measure if it was in a state in this orbit or the other orbit. But that's a little bit. I'm getting ahead of myself. So there are superconducting, trapped ion, neutral atom, nuclear magnetic resonance realizations, semiconductor, nitrogen vacancy centers, and topological and other ways. There are lots of technologies in principle, but superconducting and trapped ion are the most important right now, and neutral atom. And each of the technologies has some advantages and drawbacks, but that's just technicalities, okay? That's something I wanted to show to you. Those things are not that important. Oh, they are extremely important, but not for this lecture. I would like you to observe one thing. clock cycle. This is off-the-shelf CPU, more or less 3 GHz of the clock cycle, right? So single operation, well, 3G is 10 to 9, right? So it's 10 billion, 3 billion operations per second, quite fast. While any other technology performs, quantum technology performs a million, 1,000 operations per second. So classical CPUs are in general much faster than quantum processors, which explains why. Well, we said we can recreate classical computation on the quantum computer. So why don't we do that? Because of that, it's at least 10,000 times slower than the standard CPU. And if you look at the price tag of CPU and quantum computer, that's another story, right? So that's why it makes no sense to recreate classical computation on quantum computer. But it sometimes makes sense to perform quantum-oriented algorithm on quantum computer, which will be faster than classical algorithm, even though this thing seems like it's extremely slow. Okay, two more things, yeah. There's another paradigm of quantum computation, and Amer here is an absolute expert in this type of computation, and I will explain it to you by hand waving. It's not a gate-based computation, so we do not apply subsequent gates. But what we do is, well, it's a non-universal way of computation, so we cannot do any computation with so-called adiabatic or quantum annealing. And well, it's let's say purely quantum computers which do purely optimization problems. And the idea is, maybe not only hand waving, I also use a chalk, that sometimes sometimes, quite frequently, we wish to find a minimum of the function which is very hard. This is not a very hard function, but you get what I mean. And luckily, we can evolve physical systems in a very particular way. If we prepare a system in a minimum on very easy function, and we have a way, and usually we have, to evolve slowly this function to such function, okay, so there are some intermediate steps, okay, and in the end evolve it into some very hard function, then we are guaranteed that we'll be in the minimum, okay? So adiabatic quantum computing is all about evolving the system, the easy system, to a hard system to obtain the solution naturally, but there are some drawbacks, and the biggest drawback is we cannot do it fast, okay? And that's from a physical point of view very natural, because if we change the system very rapidly, we'll excite the minimum state. The ball can just jump somewhere, right? So we have to do it slowly, and there's a limit that the time of computation has as a so-called 1 over square of so-called energy gap. So let's say 1 over the energy difference between the minimum state and first excited state, okay? So for many problems, you will have to do it very slow, and that prohibits sometimes from obtaining speedups, but not always. Okay, last thing, how you can access quantum computing devices. And maybe it's a little bit still too early to access the quantum computing devices, but I will nevertheless tell you. So any big cloud provider gives an opportunity to access quantum computer, send a job through its API, so you can use Amazon. Not sure about Google because they have a quantum computer, but I know it is that open as other. Azure, IBM. With this difference that IBM are free up to 10 minutes of computation, which is not much, but you can play around with it. And they have their own quantum computers. Azure and Amazon, they just outsource computation to other companies that have quantum computers. Google has its own computer system, I think, but I'm not sure you can easily access that. And Amer mentioned to me that Jülich has lots of quantum computers and will have even more, right? So they don't advertise it that much, but you can contact them and get some access of Hilbert. Sezga, yes, yesterday you heard QMIO, right? And one more thing about the quantum machine, there's a T-Wave company, very famous in the field, that gives you also some limited free access to their quantum annealer. And yeah, let's have a break. Thanks a lot. This lecture is about showing you some more complicated circuits and trying to explain what they do, why they do it, and what's the whole logic about possible speed up with quantum algorithms. And first, I would like to introduce some kind of a division in quantum algorithms. There can be many ways to divide algorithms, but from the point of technology readiness level, I've came up with, well, smarter people than me came up with the division of the MISC algorithm. Well, I will talk about MISC in a moment, but in general, those are near-term algorithms. So the algorithms which should work well on the current devices that we have, or the devices which we'll have in the near term, couple of years, and fault-tolerant algorithm designed for fault-tolerant quantum computers, which will be big machines with error correction implemented, and we are still, I don't want to give you any time scales, but years away from having those kind of machines. Okay, and we'll focus today on, I think, 3 elements from those lists. And as you will have a whole lecture about quantum machine learning by Amer, I would like to show you the logic behind this long-term algorithm, two of the most famous algorithms, so Jagiellonian algorithm and Grover's algorithm. Probably the most known is Shor's algorithm for finding prime factors and breaking the RSA encryption, but that's a little bit too hard to do in half an hour. Nevertheless, those two will be enough to show you most of the features of quantum algorithms and why we believe they can be faster or better than classical algorithm. And I will start with Jagiellonian algorithm, but first I believe we have to introduce the concept of query gates. So query gate is the gate which computes some function given an input. Okay, so basically calculating the function value. And in the classical world, well, let's just compute the function value. In the quantum world, in order to implement such computation, well, we have to stick to reversibility. So, how we do it? We prepare input qubit registers, output qubit registers, apply the gate on the whole system, forget about it, just like in the NAND gate, and we'll have and just read the output qubits, which will be the input state, probably just 0, plus the function value. This class is the modulo 2 addition, okay, so the one that classical computers do. And another thing is that another definition, let's say, is the definition of a balanced function, which will be important for Deutsch-Jossa algorithm. And the function, balanced function, is a function that will take some big string, n-dimensional big string, and outputs 0 or 1, and it is balanced when half of the outputs of all possible inputs are 0 and half are 1. Okay? That's really, I think, easy concept, right? There's another type of function, constant function, where it's only zeros as an output or only ones as an output. And as you probably see, the subset of balanced and constant function is much smaller than the set of all functions of this form, right? Because we can have functions which are not balanced and not constant, right? So, for example, a function which has for one input gives 0, and for all other inputs gives 1, for example, and this is not balanced and not constant. So a very specific set of functions, but well, that's on what kind of functions Deutsch-Jossa algorithm works. So you already probably anticipate that this algorithm is not very useful, but it's very good for educational purposes, and that's why I start with it. And the problem statement for the algorithm is that given a function which is balanced or constant, so we already know that it will be balanced or constant, determine whether it is, well, which property it has. Is it constant or balanced? And the question is, how can we solve this classically? And classically, well, in general, when we have n-bit strings, there's 2 to the n, the size of the input space is 2 to the n. Right? And in the classical case, worst case scenario, we'll have to calculate the function for half of the inputs plus 1, okay? Because we can, the worst case scenario is, we want to check if it's constant or balanced. Let's say we have inputs, the string of 2 bits. So 1, 1, okay? And for example, for this we get input 0, for this we have input 0, and we already checked the half of the possibilities, and we don't know if it's constant or balanced, because, well, it can be still, if there are 2 ones here, it will be balanced, or 2 zeros, it will be constant. So we need to measure 1 more than half of the inputs, and we, for example, get 1. So we say, okay, so we know there's a one value which is different than all the others, so it is balanced. So we automatically also know that this will be 1. So the worst case scenario in the classical, we need check half of the inputs plus this 1. Of course, we want to do it for much bigger inputs, right? And miraculously, like really miraculously, quantum computer can solve this not in half plus 1 queries, but in one simple query. And we'll see how this works. But it's much better to start with not Deutsch-Jossa algorithm, but Deutsch algorithm, which is Deutsch-Jossa algorithm, but for 1 qubit, okay? And then we'll extend the idea. So let's see the Deutsch problem. We have 1 qubit function, so or 1 bit function, 0 from 0 or 1 to 0 or 1, and there are 4 possible functions of this set. Either it maps everything to 0, so f of 0 is 0, f of 1 is 1, or it maps everything to 1s, or it maps, or it performs like not, identity, 0 to 0, 1 to 1, or not, 0 to 1, 1 to 0, okay? There are 4 possible options, and actually they are all balanced or constant, so we have no other options. In this case, if we have like bigger functions here, then it will not be the case. And what's the input? So we use a Hadamard transform, so create a full superposition of the possible states in a 2-qubit system and apply to this state, which is full superposition, the function. Okay, so basically what we'll do is calculate the function in one step on all possible outputs, right? So we have a linear combination of state 0, 0, linear combination of state 1, 1, with a minus that. It's important, but not for this argument. We perform the query gate, and for each part of the linear combination we get function value, okay? And, well, if we then create a product of those 2 qubits, the first qubit state and the second qubit state, we can write it as first qubit being in the state 0 plus this term of being in a state 1 plus the second qubit, which doesn't matter as that much. And you will see that this is a -1 to the power of a sum modulo 2 of the function that you would like to find. And if you run all the possibilities, you'll see that if it's a function 1, okay, then you will get 0, 0, 0 plus 0 in modulo 2 addition is 0. So this state will be 0 plus 1. If you do that for function 4, you will get 1 plus 1 modulo 2, which is 0, so the same case as here. You will get again the same state, 0 plus 1, okay? So constant functions will give you just the plus here, and if you apply it to F2 or F3, you'll get 1 in the power, so it will flip sign here. So for a balance function, you'll get 0 minus 1, okay? And if you do Hadamard transform on this state, it will actually change to the possibility of obtaining either 0 for constant functions and 1 for balance functions. So basically, what we are doing is what physicists would say constructive or destructive interference. We make the state to have this structure, to catch the structure of balance or constant function within the phase of the state, and this will actually produce, will be able to produce the one query answer to whether the function is constant or balanced, but that's just for 1 qubit. You can extend it to many qubits. How we do it? Well, basically the same way, but the last qubit. Well, you add one last qubit, and yeah, and well, you can apply it to any 10-bit function, and after one measurement, you will get either with 100% probability, either 1 or either 0, and you will know if it's constant or balanced. Okay, so that's rather a short introduction to the logic. So I will just recap what we've done. So we've used something which I called this before quantum parallelism. So we created a state on which we were able in one go calculate outputs on every input possible, okay? Because we created a linear superposition of all possible inputs, okay? And then apply the function to, in one step, to all possible inputs, and we obtained all possible outputs. So we were able to check the function globally, but the problem is that, usually the problem is that such output state is again a linear superposition, and when we measure, we will not gain all the information. But with smart use of gates, we can amplify the probability of checking if the function has some specific structure or not. And in this case, you can do it with 100% probability that with a single shot, single run of circuit, you will see if you see 1, it's a balanced, I think. If you see 0, it's a constant function, okay? So that's a very rare case that you can use quantum parallelism, that your measurement tells you all the information that you need. And that's only because of the structure of the problem that we assume it's either constant or balanced. Not very useful. Nevertheless, the Grover algorithm is believed to be extremely useful algorithm when we will be able to implement it. And I'm not a science communicator. I'm not a person who does lectures like in an understandable way, but I try my best. But there are smarter people than me in that domain. And I don't know if you know the YouTuber Free Blue and Brown. But he's awesome, I would say. Grant Thompson, I think he's called. He actually created his own Python library to animate those movies that he creates. I even use it, and it's really nice to use. And he performed also recently. He released a very nice video on Grover's algorithm that explains it much better than I will ever be able to. So that's my recommendation for you if you want to know, draw some good general conclusions about quantum computing while inspecting the Grover's algorithm. But nevertheless, I will try to explain it to you right now. And the Grover algorithm answers the question of unstructured search. So let's again, let's assume we have lots of elements. I don't want to say in a database, but we have a set of lots of elements, and we want to find only one particular, and that one particular is marked in such a way, well, we have some function, I don't know, a Boolean function with gates that gives 1 only for this one element. We don't know anything about the element, and it doesn't have any special properties, except that we have some unknown function that it's hard to calculate, and that function for that single one input element gives 1. Okay? Actually, the Grover algorithm works also if more elements are 1, but we'll still focus on the simplest case when we want to find one element in 2 to the n element set. Okay? And in the case, and this is the problem of unstructured search, and in the case of the classical solution, it's a NP-hard problem, I believe. So it's exponentially hard to find such element. Well, because you have to randomly look for it, and well, so in general, it's case like 2 to the n, so the number of input elements. But Grover algorithm provides a way to find it in square root of this number of tries or function evaluations. And in this particular case, you have to believe me that we are able to efficiently implement query gates which are not of this form, but which perform very specific thing. It ZF and ZU with the Hadamard transform from both sides. The ZF performs a reflection around the universe superposition of states. Soon I will provide you geometric interpretation so it will be easy to see. This transform will reflection about so this universe superposition which are not solutions. So universe superposition except the state with solution, and universe superposition around reflection around universe superposition of all states, and that's. And what we do in Grover algebra, we subsequently apply ZF and this U with Hadamard, square root of n, square root of 2 to the n times. Okay, so that's why this speed up is visible here. There's a floor here and phi, that doesn't matter. So, what happens? I will just show you a very geometric way what happens in Grover algorithm. And what we first do, we do a Hadamard transform, and we'll see that in here. So, what's on this axis? On this axis, we plot our solution. We don't know it, but we know that the solution state is somewhere here, and we plot this direction. In this direction, we plot on one dimension, let's say, but all the other states all the other directions, okay? Well, we have to resort to some projection, but so this is all the other states, and this is the solution. And when we create the uniform superposition of all states, it will be mostly in the direction of all states which are not solution, but the solution will be included in uniform superposition, so it will have a small coefficient toward the solution. Does it make sense? Okay, yeah, hopefully. And what do those applications of those transforms do? So, as I said, ZF, this query gate, does the reflection around the directions which are not solution. Reflection, so I mean that the vector is reflected with respect to this line, okay? And actually, what I plot also is the probability of measuring our solution and the total probability of measuring any other state. Okay, so we've just reflected our state with respect to non-solutions. And then we reflect our state with respect to uniform state, okay? And what we see that we started here, went here, and now we reflect with respect to slightly different plane. So our resultant vector is slightly more pointing toward the solution, okay? It moved a little bit up. And if we apply it more and more and more and more times, you gradually increase the probability of finding the solution. It's still quite low, as you can see, but we know exactly how many times we have to do it. It was this pi over 4 floor of pi over 4 of the square root of the number of inputs. And, well, we can go on. You can see the probability of obtaining the solution is growing until we find an optimum, okay? And we are not guaranteed that our vector will end up exactly to be vertical, so pointing exactly in the solution. But in general, it will be exponentially likely that after applying so many iterations as I told you, that this probability of obtaining any other state will be exponentially suppressed. So basically, you can run your algorithm 1 time, 2 times, maybe 3, 4, 5, and if you for every time you will just find the same solution, the same output, then you'll know, yeah, okay, I measured the correct solution. And you can go even further with that and start reflecting here, but what you'll do is start to make circles and decrease the probability of obtaining the correct solution. So that makes basically no sense. Okay, and this procedure is called amplitude amplification, which basically says that what you've done is amplified the probability of finding some solution that you're looking for. Okay, so that's geometric point of view of Grover's algorithm, and it is believed to be. It's a very well known problem, the unstructured search problem in classical computing, and I know that there are smart mathematicians who actually proved that the square root of 2 to the n scaling, so the Grover scaling is the optimal one. You cannot go better, and probably classical computing will never be even close to that. So that's one of the algorithms that can be useful, and seems to be the one beating the classical computation. However, we are not yet able to implement the algorithm because it consists of many gates, and this can be troublesome because right now our devices are noisy. And the second thing is that, I don't know if quadratic speedup is enough, because we already talked that the quantum computation is 1,000 times slower. So if you look at the computational time as a function of number of bits that you use, colors. The classical computing will scale. That's but quantum computing will scale something like this. Okay. So it will start with quantum classical time. Okay, so this point where quantum algorithms work faster can be for very huge n that will be still outside of reasonable times for us to computation, like 300 years. I don't know. Okay, so nevertheless, theoretically, this algorithm is better than classical and is optimal. So, we can hope that this will be useful. And can it be? Yes, any optimization problem that we don't have any information about what's the optimization landscape can be discretized, and the global algorithms can be a way to find this solution, right? Minimum. Okay. I think that's more or less time for the session. So I will just. I believe I said everything about those two algorithms, and something that I would like you to prepare for the after lunch sessions. So those two algorithms were designed for fault-tolerant computers, which are far ahead, let's say, without any time scales, because I've heard lots of estimates, and I don't believe we can give 10, 25 years estimate when the error computers will be working on a big scale. But there's this idea of NISC that I mentioned at the start of this lecture, which now I will decipher the acronym: Noisy Intermediate Scale Quantum Devices. And the guy on the picture is John Cresfield, who actually introduced this term. And he observed something, the state of the art of quantum computing right now, or actually 2018, but let's say right now. And so our computers are exposed to noise. So it's very likely that with big computations, will introduce a lot of noise to the computation, and basically the output will have no real connection to the input, right? You will get a random number generator. But the error rate is more or less on the 2 to minus 3, 10 to minus 3, 10 to minus 5, okay? This limits the size of the algorithms we can perform, and we have no error correction, so we have to live with those horrible probabilities of introducing errors. But that roughly corresponds to around being able to do 100 gate layers, and to, well, more or less, I'm simplifying, to, we have access to more or less tens to few hundred physical qubits, those qubits. And if we do the math, we'll realize that, well, if we, for example, look at the 50 qubits quantum computer, we have in CESGA 32 qubits, right? So we are quite close to that. The size of the vector space in which we will be working is 2 to the 50, which is 10 to 15, huge number. And that's actually the dimension that no supercomputer can calculate in such high dimension. That is just too big to any classical supercomputer that we have. So he thought that, well, maybe we can use around tens of qubits, knowing that there's a possibility of error, and knowing that restrict ourselves to not that many gates, but still run those kind of algorithms, or design the algorithms that will, in which will have the noise, the possibility of conflict or something like this will not completely destroy the algorithm that will be running. Okay, so he proposed that, okay, let's use tens of qubits on the physical noisy devices, and we have a chance that those setups will be already that hard to classical computer that will be able to do something useful and faster than classical computers. And he coined the term noisy intermediate scale quantum devices, and within this paradigm, quantum machine learning fits in, because in many cases, introducing a noise, for example, to computation of quantum machine learning computation, well, can be even beneficial, or does not destroy the whole pipeline. Okay, the small noise is sometimes accepted in machine learning algorithms, and well, that's where this field started, and we'll see how Amer will expose you to this idea after the lunch. So that's all from me. Nevertheless, I will stay here and help you out with any questions and problems with hands-on session. And well, I would like to thank you for the attention in the morning. And let's start the hands-on session by IBM. It's already right.
Yeah.
I'm using lots of energy.
Yeah.
Yeah.
Good afternoon, everyone. That's good to see some enthusiasm after this heavy morning, very important morning of introduction to quantum computation, quantum algorithms. Now, the afternoon will be a bit smoother, let's say a bit more, more application-oriented, less theory-oriented. So Artur is a physicist, and he tackled the hard part. Now I'm an engineer. I will be mostly, see quantum computing from my user perspective, and show you how you can use it to do something, let's say, practical. And in particular, we'll be focusing on this very broad and a hot topic called quantum machine learning that I hope you will be at least understanding a bit after this talk, which is, I mentioned, the first one here in the afternoon before the hands-on session where we will go a bit deeper into some of the quantum machine learning models that we present today. So here's a summary of the main application of quantum computing. So here I mentioned quantum simulation, which basically means using quantum computing to simulate quantum systems. But quantum computers are quantum systems themselves. So if you find a way to basically map real quantum, let's say a phenomenon that they can describe by quantum physics using quantum computer, there you have the best matching between the computational power of quantum computing for something practical. Then we have quantum cryptography here. This is research topic, probably the main application that actually triggered the quantum hype at some point. So this short algorithm that Artur mentioned is this very fast and efficient algorithm to find prime factors of a number that will ideally break the main cryptographical systems nowadays rely on this aspect. Then you have quantum optimization and quantum machine learning that are basically computational machine learning using quantum computers. Today we'll talk about quantum machine learning. Here are the questions that you may have, and we will try to answer. So, first of all, what it is, how do we work with data? Okay, how do we encode data into quantum circuit to do quantum machine learning? What are some models that would be nice to know so that you have to get a grasp of the field, and why should I even use it? So what's the advantages and drawbacks? First of all, I hope you have heard of the term machine learning, right? I mean, I've seen some very nice topics that also go well beyond the basics of machine learning, but I mean, in principle, machine learning is this, okay? Finding patterns in data. So we have, say, let's focus on the supervised, setting. We have data, okay, so that we want to try to understand the patterns from, and especially we have, let's say, a vector or set of features that describe something in the world, and a set of labels that give a meaning, a class, to the piece of data that we have. We want to train a model, okay, that basically finds the connection between the features and the labels. And with training, we try to find the best model within this class of models that minimize certain loss, which the idea is maximize the correctness of the prediction model, of course. And then we get a train model that is function that for any set of feature vectors, of course even unseen ones, we get actually the correct label. So far so good. It's not quantum. Okay. So from this definition, basic definition, we can easily find the definition of quantum machine learning, which basically means finding patterns in data using quantum computing. Quantumly. So quantumly, I swear, it's a word. Don't come here. So, yeah, in this case, what we, the quantum part of quantum machine learning is in the model. So, this function that maps inputs and outputs is quantum function. So, let's say a set of operations performed by quantum computer. Okay? See, so very nice correspondence. There is one thing though. What about the other parts of machine learning? Why do we need to have the model? We can have something else that can be at least done in a quantum way, or at least related to quantum. For example, that shows me the data. So there is such a thing as quantum data. We don't really use it because we cannot store quantum data. There's no quantum realms, although we know what quantum realms are, we don't have them currently. So we cannot store and work with quantum data and say source. But ideally, there may be a case where we can use quantum sensors to encode quantum data and process them immediately. So there are some, in some cases, we can work with quantum data. It's not for everyday use, it's not for general machine learning, but ideally, this is also quantum machine learning. But using quantum data. But then, what about using quantum models to find patterns in quantum data? That's also quantum machine learning. So there's three definitions of quantum machine learning that we can find, and they're basically just derivation of the original definition. So this is basically the starting point of our discussion. Finding patterns in data using quantum computing. Knowing the differences between classical and quantum computing and the way we handle data. And hopefully doing this so that we get an advantage finding better patterns or finding them quicker or with maybe some data encoding that works best for certain parameters instead of classical parameters. And this is basically our goals, right? As I mentioned, quantum data is not something that we can really work with today because of the very, very difficult way to find sources of quantum data and store it. So we work mostly. So for us, quantum machine learning means using quantum models, quantum circuits mostly, to find patterns in data. That's it. Here's the letters that we will see the literature on quantum machine learning that describe these four definitions: CC, CQ, QC, QQ, depending on whether the data or the model are quantum. Where we can find, how we can, the modeling of the traditional, in the training the traditional model, how can we use quantum computing? Well, either for in the encoding and processing part of the model, and then we can maybe train the model with classical computing, or we encode the process classical and then we train quantum computers, or we have a model and we want to do inference, finding patterns, finding tables of unseen data with quantum computers, maybe in a more efficient way. So these are, let's say, the three areas where we can use quantum computing to machine learning. But still, we are working on quantum circuits, and there's no way we can we can work on data if quantum circuits cannot understand it. So anyway, even if we have classical data, basically everything we did and remote sensing and autonomy, we still have to somehow move it into the quantum domain. This is called quantum data encoding. Here I showed this is a very simple case, I think, in a piece of data in remote sensing, let's say 2 times 2 window that has, let's say, that describes some, let's say, a quantity of the, let's say, for example, here I have only 2 channels, so basically under those channels will be the digital numbers that correspond to spectral bands of a multispectral sensor, for example. And now I will show you how you can encode this very, very simple image together with label. Let's say when we have a label, we want to basically understand how I want to classify this image using, I don't know, this random set of labels. We take single pixels and we put them in a row. No matter if we have 2D, 3D representation, we always have a vector again that will summarize the total set, the amount of features we have. And yeah, we need to scale them because here, this is what I show now is called angle encoding. And what we do is say somehow fitting these features as angles of rotation gates in a quantum circuit. In this case, so hence this case, we want to be sure that for in this case we have for 8 features we have 8 qubits, and we want to rotate each qubit by a certain angle. And well, you remember that we can rotate things up to 2 pi. After that, we get the same qubit. So that's why we have to encode the like no matter how large the feature space is, we need to stay within the range at which we can distinguish between the features and rotate the corresponding qubits. Example here is we have this vector, we normalize, we scale it, and apply these rotation gates. For example, we can rotate along the y-axis of the block sphere. So we have 8 different, we have these 8 qubits will be 8 different states, each state is kind of corresponding to a real number that will describe, that will fully describe the original feature vector. Angle encoding, okay? It's not the only way to encode data in a quantum circuit. We can, for example, use amplitude encoding. I don't know if you remember, before we, like, with a quantum circuit with n qubits, we work in a feature space that has dimension 2 to the power of n. So the feature space of the circuit that is all the states that we can represent will be a superposition of 2 to the n states. In the examples where 8 qubits, we have the 8. 256 possible states. Actually, 256 basis states that are like the actual state of the quantum circuit that we have superposition of 256. So basically, what we can say is, okay, let's encode these amplitudes as the amplitudes of how these 256 basis states are summed with each other. So, again, the method we normalize according to we normalize the feature vector because states are a linear combination of basic states, but the norm of the amplitudes, norm of the sum amplitudes has to be 1. And then we encode them as amplitude 1 for the first state, amplitude second state, and so on and so forth. Okay, same example, normalize, and this is how this is done. Okay, I won't really say why this is like this, but at the end of the day, we measure this circuit sometime, like multiple times, thousands of times, and we measure the statistical distribution of the 8 states that we measure, so 0 to 1. I get an estimated probability for each one that corresponds to these coefficients. So here's how you can also encode information using amplitude. Now that in this case we have only 3 qubits, because we can with 3 qubits you can have 2 to the 3, that is 8 basis states. Every 8 basis states are enough to encode this 8-dimensional vector. Whereas in angle encoding we have to encode each feature for the rotation, like rotating each qubit, so that needed 8 qubits. Okay, what about the label? Okay, the label is just either 1, 2, like, it's basically a discrete value usually, labels. They are countable, let's say, features in a way. And yeah, there's another type of encoding called basis encoding, where actually we assign each of the values that the label can have to one of the basis states that I mentioned. So 0, 0, 0 will be 1, like label A, other 0, 0, 1 can be label 2, and so on. In the case of 4 labels, we need 4 basis states. So we have 0, 1, 2, 3. And yeah, we can basically, like, the practical way is to binarize the values. So 0, 0, 0, 1, 1, 0, and 1, 1. And say, okay, 0, 0, 0 corresponds to the first label, 0, 1 to the second, and so on. Label 3 becomes 1, 1, and that's what you do. This is the NOT gate or ASC gate that transforms zeros to ones. So output gate 1, 1. So that's the way to encode discrete values. Yeah, before we could, like with the first two encodings, we could encode continuous variables. For the case of Angular encoding, we needed n qubits to encode n values. For the case of amplitude encoding, we need log n qubits to encode the n continuous variables. Basis encoding is used for discrete variables, and according to how many discrete variables you have in total to encode, you need the feature space to have the same, let's say, encoded dimension that can fit them. And yeah, usually it's around, yeah, that's why basis states. Okay, this is just an example of how you can encode circuits. This is probably the simplest way to encode data in quantum circuits. There are more complicated ways if you need to do certain things, work with certain algorithms. We will see some examples later, but this is how it's done. Okay, so binary classification, very easy machine learning setting, okay? Finding whether the image belongs to class A or class B, class 0, class 1, Chihuahua or not, Labrador or fine chip. I would say it's one probably the simplest case of supervised classification. We want to basically find an automatic way of distinguishing two classes, which may not be trivial, apparently. So, in an ideal world, there should be a way to distinguish two classes by just tracing a line. So, features and say n-dimensional feature space can be divided by a line. In case of 2 dimensions, or a plane, multiple dimensions, or hyperplane, and everything that and feature space divided by 2, and every possible every vector for each of the sub portions of the space can be assigned to either plus 0 plus 1. Yeah, this is the mathematical way of showing it. We have a function applied to the feature vector. So the product with vector of parameters, not vector specified parameters. In this case, parameter is this, but we no matter how we visualize it, there's like training the model means finding what are the ways that so that this function will be able to discriminate between the two classes in yeah, case of super vector machine, most famous, the Pyari classifier. This is how we find the vector weights. It's an integration problem. Mostly, I would say quadratic, but inequality constraints. And yeah, this is how it works. Very easy way to there's efficient ways to optimize this function, yeah, and we are all happy. But yeah, sometimes I would say always this is not the case. I mean, not really always. Sometimes simple models can do the trick, but yeah. One of the application approaches to deal with non-separable classes is to find a higher dimensional feature space where these classes are indeed separable. It's an example of going from 2D to 3D. So if we map the points in this way, okay, so that we end up having the red points below and blue points above, we can find another plane that can still divide the feature space into sub-portions and get your, and have your linear classifier that still does the trick. Like that before. The only difference is that, yeah, you need to know what this feature map is. It's absolutely non-trivial. People can we can decide, okay, let's say we focus on a class of feature maps and we bag the parameters and see which parameters give the best result. This is the best classification result of the training set, and there you have it. So we can still optimize it fairly easily. Same things for the machine, we have theorized. So far, so good. I think maybe you're familiar with the Keller trick, I don't know. But there is this thing where, for example, with the example of the SVM, we can basically rewrite this optimization problem into another form, which is not an initial problem. But it's a maximization problem that is not on, that does not work on W but on other variables, alpha, for example. But yeah, what really changes is that now the constraints are easier. Okay, and also we can see that now working with feature vectors, we basically always work with dot products of the projected feature vectors. Basically, what we can do is, okay, so either we compute feature vectors, so they transform feature vectors for all the training vectors, and then multiply them with each other and get this quantity. But that can be very inefficient, especially if we work with high-dimensional feature maps. Or we can just find a way, a clever way, to skip all this conversion process and just make sure that we find, say, a function of these the two vectors, and that directly outputs a real value, that is, the dot product of the two vectors in the transformed feature space. This is called the kernel function, and it makes you completely skip the need to find out the feature map. We may not even know what this feature map is. This feature map may also not be, say, written in a simple algebraic form. It can be literally anything, but what we need to find is the function that computes this dot product. And then you can train your classifier. A very famous example is the RDF terminal, which basically is a distance measure between two vectors. So you have this like the two vectors one side. This becomes 0 and e to the power 0 is 1. If they are very, very far, there will be this value is 1, 0. Yeah, so this is a way to actually, like, this is one of the go-to kernels when you run SPL to build classifiers. Only thing is you have to, still check family of kernel functions so you have to optimize the gamma, but then you end up having kernel classifiers. Okay, these are called kernel methods. Methods that use kernel functions to train a classifier. What is a quantum kernel now? Well, okay, very easy. Quantum circuits that compute a kernel function. Logical, I would say. And I think that with what you know about quantum computing, you may have an does anyone want to guess at least the approach of computing the kernel to vectors? What do you have to do first? No wild guesses. Well, sorry? Yeah, I mean you can basically just use transform the vectors to the new feature space, but it can be done by that. But let's say we want to do this like quantumly. There's like dot products are like difficult to map, but basically the feature maps in this case can be the data encoding I mentioned before. Data encoding basically makes you convert classical data to quantum data, but the quantum data in the quantum space is also a space. It's also a feature space. So that also logically is a feature map. So we can encode like vector in sacred, encode the other vector, and then multiply it, let's say, and apply these weights to the initial random thing to make sure that then you multiply the amplitudes of this little space in this quantum Hilbert space. And yeah, this is basically doing like computing a kernel. But like computing at the end, if you do this, you get out a quantum state. We still need to get a real value. How do we get a real value? Well, we will get like propositional states in 0, 0, 0 plus whatever, but at the end we need a real value. And how do we get there? We decide to measure something, measure a quantity. And usually what you measure is the expectation of a certain state. So you measure it, you measure how many times, usually you need to count how many times you get that state, and say, okay, the probability of getting this state is 10%, so the expectation of this state is 0.1, and that's your cutoff, that's your number. So you need to encode the data, encode two vectors, so run the circuit with the encoding session. For example, the encoding I showed before, but when you have an encoding, and then measure the expectation of a specific state, or a specific, this is called observable, because we are going to observe the circuit, so understand, like measure what is happening in the circuit, what is the state of the circuit. And that's your value, so it can be basically it's a number, it's a real number. That is your kernel. What this kernel means, what is the original feature map, the corresponding feature map in the classical domain, that's really hard to tell. This is just totally different way of dealing with data. So, but still, it's a kernel. So one would argue, okay, let's try and see how it works. Yeah, as I mentioned, basically everything in quantum machine learning can be summarized as encoding data into the feature space of your quantum system, and then computing, measuring something, and extracting information from it via, for example, this kernel method. So you can access this kernel value by measuring the circuit. And it's a really straightforward correspondence, and this is one of the reasons why quantum kernels are so popular in quantum machine learning, because it's a very natural way to think of quantum machine learning, because how quantum computing is defined, it's basically one-to-one with kernel methods in a way. And yeah, some people argue that quantum machine learning there's always a kernel method within any quantum machine learning model, even if it's not written clearly, but there's a way to get to that. Arguable nowadays, someone was saying, well, you're not looking into all the classical kernels, but that's story for another time. So, Artur did a nice work on quantum kernels. This is an example of how you can work with that. So you have kind of features. Okay, in this case, features are I started from say segments, batches of data, just because we don't want to end up with extremely large training sets because there are some limitations in running quantum machine learning nowadays, the dimensional data. So we want a small training set. And you encode these points into the circuit with rotations. You can encode them, full stop, that's your kernel. Or you can say, like we did for the RBF before, we can parameterize the kernel, maybe with the gamma like before, so making sure to have a family of kernels that you can test, and then take the best one. This is what we call trainable quantum kernels. Okay, so on fixed kernels on fixed functions are trainable. Again, you vary parameters of other layers, other quantum layer, and find the best parameter set according to specific method. Basically, you want to maximize the similarity between the computed kernel and the ideal kernel. Whatever ideal is, okay, so we want to maximize the performance of the training set and the accuracy of the training set. And then you get your trained kernel that you can then use to compute the kernel with new unseen vectors, encode it with the optimal parameters, and then you can run the operations. That's it. I don't know. If you have any questions for now, let me know. This is probably the most important quantum learning model. So, any questions or comments? Just let me know.
Is there different models for quantum? Basic machine learning has different methods and different models. But in quantum, is there a lot of models?
It's a jungle. Quantum algorithms are a jungle. There's so many different. So here I argue that every model can be converted to a kernel method, but it's just one way to look at it. Kernel methods, for example, they require you to compute the kernel between every possible pair of training examples. So that's a bit inefficient. There are ways to avoid that so that you don't need to do this. So you can write other quantum algorithms that are maybe more time efficient. So there's you can still reformulate the model and write and do different things that I will show you now. Then I will show you a second example of quantum machine learning model that is a bit different. So this equivalence among all possible quantum machine learning models is just theory, but then in practice. Also ideally in classical machine learning, you don't need many layers to being able to encode any possible function in the world. Ideally, even small networks can be vector classifiers can approximate any function, but maybe that's not the most efficient way to do. So maybe you want more specialized models and say quantum machine learning. Thank you for the question. Okay. So far, so good, I guess. I had a timer here before, but now I can't see what time it is.
Yes.
I'll just get my clock. We are going. No problem. Okay, now. We went from the classical to the quantum world to describe quantum kernels. Now we'll do the opposite for the next quantum machine learning model. I will first tell you what it is in the quantum world, and then we'll find a counterpart in the classical world. There's a class of algorithms, but not necessarily machine learning ones, but a class of quantum circuits called variational quantum circuits, or variational quantum algorithms. They are Pyari circuits, so with gates that can be adapted and changed according to a parameter. For example, the rotation, I showed this before. In which you measure a circuit, you find value of a cost function, and then you update the weights again according to the gradient of this cost function, so that you at the end you want to minimize the value of the cost function. Well, this is very looks very easy and honestly familiar to me. I don't know if you can really guess what I'm able to say, but yeah. We want to perform quantum operation, but we don't know the exact gates to use. We can parameterize them, check whether the parameters do what we want to do, find the gradient, and follow the gradient downwards, and you can go back and see whether at the end you can converge and find out the best set of parameters to perform the operation. Yeah, okay. Where is, like, how can we do quantum machine learning with this? Well, we can again encode data, like for the kernel. In this case, so we have two sets of inputs, so the vectors and the parameters of the model, and we execute it. We find a value of some cost function, minimize it, get to the set parameters, and then we get a circuit that has fixed parameters but takes any feature vectors input. You can use this circuit for classification. This is called variational quantum classifier because it's trained variationally like a variational quantum algorithm. The gradient I mentioned is not just an estimated gradient. You can actually compute the exact gradient of according to the so with respect to the parameters by running the circuit twice. Once with that specific value of the parameter plus pi f, and that value minus pi f. So you shift this parameter by pi f and minus pi f plus pi f, and yeah, the semi-difference of these two values is your gradient, and you can update the weights accordingly. Really, guys, if you don't see this now, like, this is really exactly what classical networks do. So you somehow have an input layer, has some weights, can distribute it in very fancy ways. And at the end, you measure something, you measure the expectation of some quantum state in this case, you measure integration function based on the value of the inner layers. You compute the gradient according to the say, respective parameters, update the parameters, and so on. This is how deep learning is done. And we have the same exact thing in variational quantum classifiers. This is why variational quantum classifiers are also called quantum neural networks, because they basically work the same way as classical neural networks. Again, as classical neural networks, we can think of more interesting architectures here as well. We can code circuits differently. We can code them not only in the beginning, but also we repeat the cycle multiple times, have features parameters, or longer set of parameters, or measure something in between so that you keep working with the others. There's like really a lot of ways to build new models. And yeah, basically this is what you can do with quantum networks. Find different ways of repeating and adapting to this core principle of variationally training a quantum circuit. Ideally, you can also say, okay, I really like my convolution, my classical convolution network. Is there a way I can really keep that for extracting the features and then use the features, is to say, process features, convoluted, the convolution features to train a quantum network? Yes, you can do that. That's called hybrid quantum classical neural network. And these are also things. This is an example of Alessandro's work. There you go. He tried this with satellite images. Yeah, because as I mentioned before, we really work with high-dimensional data, high quantity, and lots of images, lots of pixels. So the single feature vectors can be really a lot, and it's difficult to work with them efficiently in the quantum world only, because encoding circuits also takes time. You need enough qubits to encode them. So I will briefly mention all these limitations now, but I will explain them later. And that's why we want to use a way to encode, using convolutional layers, encode the initial images into a quantum circuit, for example, and you have with only 8 features. And 8 features can be very simple to encode, and then you can measure the expectation of different states. So you can measure different outputs, which then have new features that you can use later on to perform other measurements, other calculations in the classical domain. And funnily enough, that's why I call it quantum neural networks, because again, you can still work with them, adaptate them by using gradient descent. Altogether, the back propagation can really work very well between classical and quantum layers. And and you can optimize, you can train this neural network like classical via the parameters there. So basically, the sky's the limit. This is what I just said. These are 2 examples. I mentioned the other direction kernels and dimensional simulation with quantum networks, hybrid networks, in Earth observation. There's many more, but I would not be able to explain them in detail here, but I will show you some examples. You can, for example, extract features with quantum computers and then train a classical model with those, instead of extracting the features classically, training a quantum model like I did before. We can find efficient ways to embed image satellite images in quantum states. I told you before, angular encoding, amplitude encoding, basis encoding. Those work with any set of data, but maybe with satellites, there are ways to do more efficient ways to encode them. Maybe a way to ensure that you don't have just a meaningless long vector, but maybe you can connect the features so that features of the same pixel are together and processed together, instead of just spreading them in this long vector. But there's many ways you can actually make clever embeddings with quantum computing. Similarly to the feature estimation part, we can build, say, hybrid quantum classical neural networks, where you train the convolutional part of the circuit done of the network performed by a quantum circuit, which is called convolutional layer. We have here, and now it's probably the go-to way to explain it, using quantum convolutional layers to extract features from the whole image. That's inefficient, because I told you, working with whole images in quantum circuits, it requires lots of quantum resources. So yeah, this probably is, like, operation will be something that is maybe less quantum ready nowadays, but we can still simulate the behavior of quantum computers and still understand how the models work. Again, like, there's a thing such as quantum diffusion models, quantum gaps, quantum transformers. There's really anything like that. Every day you see new models with things, and but there's a work on quantum diffusion models where that takes up like image generation. Yeah, and so much for standard approaches. This is all within the domain of quantum models. So exactly like making sure that you you create and predict a classifier with quantum computers. But you can also take completely classical classifier like an SEM and optimize make the optimization faster using quantum computing. In this case, we don't have a quantum model, but we have still a classical model trained with quantum computing, so that the training becomes faster. And that's something that quantum annealing can do. Quantum annealing is a class of algorithms belonging to the Delilbasic, so non-gate-based quantum operations that can quickly find the minimum of a function. And if you encode the minimum of a function as the optimal value of the SVM, the optimal W's I showed you before, we can find, we can train a classifier very quickly. Like, this could be a whole one-day lecture, quantum annealing, how to encode the program so that the optimization does this, what I just said. But yeah, since this is not gate-based and we want to mix up like quantum computing approaches, I'll just throw it there. Although this is what I did. Most of it so far, but I will have to take aside my passion for quantum annealing. There's no space for it. But yeah, that's also that. So if you want to maybe read more about this and about what the models I mentioned, papers out there, just in this collection of them, that you can share. And you also have the slides. Actually, have them already. Why? Why should we actually? Why do we do a full day lecture of algorithm? Because classical machine learning works just as fine. The question of asking why is perfectly natural. I'll give you 6 reasons why quantum machine learning is interesting. First of all, one of the powers of quantum circuits is that we work on feature spaces that grow exponentially. So, with relatively few operations on data, we can end up with quantum feature spaces working with like very high dimensional feature spaces that can be used to discriminate the classes better compared to equivalent classical feature map, which means in a higher specificity. These quantum kernels, for example, as I mentioned before, can, with very simple operations, you can already go to high-dimensional feature spaces. The classical way to simulate such a feature map can be very difficult. You really need very high number of basis operations. Sometimes some quantum feature maps can be much harder to simulate. And those are the ones that actually we really care about, because if there's a quantum feature map that is equivalent to the RDF, why bothering again? But some feature maps can be complicated, and if there's a way we can make sure that the difficult ones are also the ones that the optimal ones for the classifier, well, then you have quantum advantage. I didn't really talk about this, but with few qubits, we can work on dimensional quantum classifier with fewer parameters. Today I had only a parameter per qubit. And yeah, quantum in deep learning, sometimes we talk about millions of parameters, not more. With like really a much lower number of parameters, you can still achieve the same performance. So like, in this case, the training can be like a number of epochs needed to converge can be much lower. I think Francesco did something that like show that you basically the number of epochs needed is, but like the number of parameters is like 100 times more for the classical circuit compared to other convolutional circuit. So yeah, I have a reader for post the data on PhD system. There are like same as for the high-dimensional quantum kernels, the highly similar quantum kernels. You have some theoretical values on some types of models. This probably approximately correct distribution learning. I will say one more word about this. There you go. That's demonstrating quantum advantage. Some data can be better encoded in quantum circuits, for example, complex data, or certain distributions, or quantum data that is started by, for example, quantum sensors. And then, last but not least, these things are very new. Quantum machine learning has probably less than, maybe within a decade, we have seen most of the work on quantum machine learning. It's still mostly theoretical. There are working applications, like most everything, but yeah, we really need to explore quantum machine learning, understand, find a way to describe why a model is better than another. And we can do this theoretically, yeah, this is what has been done, but practical part can also be relevant, even more important sometimes. For example, deep learning really started to shine when we started using it, and we had the hardware to use it. Before that, wasn't really interesting. So maybe once we get the hardware to extensively run experiments with quantum machine learning, maybe we'll have a great one. So good to be prepared for that time. It's not all nice, not all easy. We don't have the hardware, as I mentioned. We have some hardware, but limited number of qubits, and mostly noisy hardware that will not allow us to run too many quantum operations before making a total mess. Because the noise will be so high that we won't be able to, like what to measure is basically just thermal noise. And we can set some degree of noise in quantum machine learning, as Artur mentioned. This is so still, no noise is better, but some noise is not bad. Sometimes it could even be beneficial, but I digress. Maybe working with small, shallow circuits is the way to go nowadays, like for the near future. You can still do something with it. We've seen some examples. So it's a limitation for now, but won't be in the future. Then there are some theoretical limitations. Quantum kernels sound very nice, but in practice, we'll notice that when we work with high number of qubits, so when we want to calculate the kernel of high-dimensional vectors, hundreds of vectors, of features, for example, in case of hyperspectral images, if you run the same kernels, so the kernel between pairs of feature vectors, the results will be all very similar to each other. We won't be able to actually detect any patterns in the data for many reasons. Mostly, there are many reasons. I won't probably go much into it, but what happens is we cannot train it because the classifier will have an even kernel matrix that will not tell anything about the data. So there are ways to overcome this limitation by changing the formulation of the kernel and introducing data scaling. Yeah, this is a problem that we should look into. And then for the case of quantum neural networks, unlike classical neural networks where we know that we will always converge to the optimal set of parameters, this is what theory says, although in practice can be difficult, but yeah, ideally if you run the model long enough, you will get there. With quantum neural networks, this is not really true. I mean, sometimes there are ways to understand when, but happens that the gradients just are zero. No matter which parameters, set parameters you choose, the gradient will always be zero, and you can't find like a way to descend to the optimal values because the parameter landscape is flat. These are called parameters. I wish that there was a better way to say, picture this phenomenon of not being able to go to the optimal solution, and I found this. This is exactly this explains exactly what variables are. There you go. Hope you like this small introduction. You can now enjoy the break, drink some water, reflect on these, especially on these two magic models I told you about, quantum kernels and the quantum neural networks, because we will be trying to implement them. Let's see how it goes. Yeah, thank you for your attention, and feel free to ask any questions.
Any questions?
You said that one of the advantages of the quantum machine learning models is that you can improve the expressivity of data set because you have like more features. But the curse of the dimensionality is still being a problem here or not?
Well, yeah. SVMs avoid this curse, like as we know. You don't need as many examples as number of dimensions. But that's, yeah, based on these networks, yeah, definitely this is, for example, one of the reasons for the environmental phenomenon. Yeah, yeah, it can be an issue. Yeah, there are ways to overcome it. There are ways to make sure that you don't use maybe the whole space. You find a clever way to use it so that you don't have this problem. Yeah. So yeah, it is still an issue. Yeah, very very good point, and exponentially growing problem. But yeah, one of the research topics is how to avoid this, and there's still an open question, like many others in quantum machine learning. Open questions, open problems keep arising. This is the one of them, I believe, right?
Sure.
What do you, no, I'm talking to Artur. Can you confirm?
Yeah, the problem is that I haven't heard the whole question. So.
Is there the curse of dimensionality in quantum machine learning? Like, is a problem working with so large feature spaces?
It is. Yeah, absolutely. So we have a curse in dimensionality in the classical machine learning, right? And there's also the vanishing gradient problem that is also very similar to the problem in quantum neural networks. Mm-hmm. However, it seems like, well, because we have this exponential scaling of the size of the available space, it seems that the problem is much more profound, and there are many ways to avoid that, okay? For example, you can use symmetries of the problem to implement your data on a part of the Hilbert space, or just restrict, well, in general, restricting the dimensionality of your space. But, well, then you're start to run in circles, because the initial idea was to use the very high number of dimensions to find expressible models, but it seems like in high dimensions you encounter some problems, so you decrease the number of dimensions, but well, we started with the idea to increase the number of dimensions, right? So in general, there's a statement that as you reduce the Hilbert space, reduce the feature space, you allow for classical simulability of your models. Okay, so it seems that you can start to simulate the same things on the classical computer, which is usually, let's say, more time efficient, right? And
we don't want that.
Huge, and we don't want that. So a huge, most important question is whether we can find a sweet spot where we do not have classical simulability, so we have such a huge Hilbert space or part of the Hilbert space that it's hard to simulate on a classical computer, but does not yet lead to such a severe problems with vectors of dimensionality. Right now, it's an open question whether such sweet spot exists or not.
Thank you.
Thank you very much.
Thank you.
Thank you. Sorry. Yeah.
We need the notes because I closed.
I had no notes. Only thing is I didn't have the clock, so I had to go and take the other. But I think that's fine.
In fact, this clock is. Yeah, this is okay. Yeah, you have one.
Yeah, I didn't see numbers, so I couldn't really connect that was a clock. Sorry, but I was.
No problem. I closed it because we are recording this screen, so we are recording a black screen.
Absolutely.
Yeah.
No worries.
Don't worry.